All right, welcome back. This is an introduction video to day 17, in which you're going to be working on inverse trig worksheet 3. Once again, like yesterday, we're going to be using a lot of formal trig identities to help us evaluate these problems. So you'll see the sum and difference identities and the double angle identities. So you want to keep a sheet of those nearby to help you with the problems. Okay, so let's take a look at a couple examples. First example, you're going to be given that sine of some angle is 5/13. And let's just say that this is going to be a quadrant 2 angle, which is possible if sine is positive. And what we want to do is we want to find cosine of 2 theta. That would be like our first part. And also we would like to find sine of 2 theta. Okay. Actually, no inverses involved here. Just kind of a setup for what's to come. So when I'm finding cosine of 2 theta, I can use cosines double. And there's 3 varieties, so we can choose wisely. Cosine squared minus sine squared, I could do that. 2 cosine squared minus 1, I could do that. But I'm going to choose to use 1 minus 2 sine squared. You might wonder why I choose that one. Well, I'm given sine of theta, so I can plug sine of theta in, and I'm done. So I'll get 1 minus 2 times 5/13 squared. And that's it. A little bit of arithmetic. 1 minus 2 times 5 squared would be 50, and 13 squared would be 169, and 1 minus 50 over 169 is just 119 over 169. And you're done. That's it. Not too bad. Compare that to what we'd have to do if we worked out sine of 2 theta. So sine of 2 theta, only one double angle identity to choose from. I need to do twice sine theta cos theta. So now I'm actually only given sine theta. I'm not given cos theta. So I have to work it out. Oh, that's not too bad. I need to draw a triangle. So sine of theta is 5/13. I'm in quadrant 2. I'm just going to draw a little triangle right here. I know that the y is 5. And the radius, okay, try that a third time. The y is 5 and the radius is 13. So according to the Pythagorean theorem, the adjacent side must be the square root of 13 squared minus 5 squared, and that'll give you 12. Minus 12 because we're in quadrant 2 and our x will be negative. So that tells me that the cosine of this angle here is going to be negative 12/13. So I can get that from my given information for free. So that means sine of 2 theta is twice 5/13 times negative 12/13. Okay, and now I'm multiplying all that out there. 2 times 5 is 10, times 12 is minus 120, and it's all over 169, 13 times 13. Awesome. Cool. Let's see how that can change a little bit when we introduce inverses, because it's really all about inverses. Really, the problems just look more challenging. In a lot of ways, they're actually easier. So here's what I mean. Example 2. Let's say you're asked to evaluate. It's an inverse now, so you're evaluating. Cosine of 2 sine inverse of 5/13. This is what I mean by it looks more challenging. It looks like there's a lot going on. Composition of functions in this 2, and how do we handle all of this? It's important to recognize that if we're working our way from the inside out, that inverse sine of 5/13 is some angle. This has to be an angle. That's what an inverse trig function works out for you. And let's just call this angle theta. We don't actually have to find theta. We can just kind of skip that. We don't need a calculator or anything like that. But it's the important thing is to recognize that we're being asked to find cosine of 2 theta. Not the angle itself, but what's the cosine ratio for twice the angle. So we're using cosine's double angle identity. Cosine's double angle identity would say that cosine 2 theta is cosine squared minus sine squared, or 1 minus 2 sine squared. You get to choose, right? And what we're actually being explicitly told is if sine inverse of 5/13 is theta, we're being told that sine of theta is 5/13. That's synonymous. So I plug in 5/13, and this becomes the exact same problem that I worked out in example 1, just in disguise. 1 minus 2 times 5/13 squared. All right, let's look at one more. Let's do... okay, how about this? Example 3. Let's make it look really crazy. Say you got sine of cosine inverse of 8/17 plus tan inverse of 12/5. Okay. This looks atrocious. Looks awful. 2 inverses inside of a sine function. That looks terrible. Oh, but they're being added together. And inverses are just angles. You know, our cosine of this ratio is an angle. Let's call this first angle alpha and the second angle beta. And now this starts to look more familiar. This is the sine alpha plus beta problem. So let's see what we know about alpha. A little preliminary work here. So cosine of alpha must be 8/17. That's got to be true. Meanwhile, tangent of beta equals 12/5. Cool. Let's draw some triangles so we can see what's going on here. If cosine of alpha is 8/17, then I've got my triangle that looks like that. The adjacent's 8, the hypotenuse 17. Meanwhile, if tan of beta is 12/5, then my opposite's 12 and my adjacent's 5. Okay, Pythagorean theorem. 5 squared plus 12 squared, 169. Square root of that's 13. Cool. 17 squared is 289. Minus 64 is a 225. Square root of that's a 15. Awesome. That's great. So I can now use these triangles to try to finish the problem. How? Well, it's sine alpha plus beta. And I know that sine alpha plus beta is equal to sine alpha cos beta plus cos alpha sine beta. So I can just look at my triangles and pull off the sine ratio or the cosine ratio that I need for each individual little part. So sine of alpha, I look at the first triangle. The sine of this angle is 15/17. So plug in 15/17 for sine alpha. Oh, cos beta, move to the second triangle. Cosine of beta is 5/13. Cool. Cosine alpha, back to the first triangle, but the cosine ratio this time, 8/17. And sine of beta, sine ratio in the second triangle, 12/13. Okay. And then the fun part's multiplying out the fractions and seeing what you get. Okay, hope this helps out with inverse worksheet number 3.